After Brigitte explained to you what modules are, I'm going to explain a few very special modules, and these are the compiler toolchains. And these are important in two ways. On the one hand, it is very important if you want to build software, if you come with a C, a Fortran source, or C++ source and want to build that to make a program out of that, we highly recommend you to use these tool chains. On the other hand, if somebody else, so for instance, the NAISS support team, builds software for you, they typically use these tool chains to build that software. And then these tool chains, they also have a lot of libraries which the program needs to get access to in order to work correctly. So whenever, unless it's a binary install what you're using, but if it's software compiled, typically you need to load the correct tool chain for the software to work properly. So what is a tool chain? A tool chain is a framework to build scientific software. Typically, it has a compiler and a number of libraries which are commonly used by scientific software. So if it's a parallel software, it needs an MPI, a message passing library, that is required for the code to run on multiple nodes if it's a really massive parallel code. There are linear algebra libraries referred to as BLAS or LAPARC. Many applications need that to get good or excellent computational speed. So for instance, those of you which use Python, the speed of NumPy comes out of the BLAS library. So NumPy, again, calls a BLAS library, and that you get a good BLAS library is very important for that to get its computational speed. There are also, for instance, I/O libraries like HDF5, but they are typically not included in the tool chain. They need to be loaded separately if your application requires that, but you have to make sure that you pick the correct one for the tool chain. And then if you want to get more advanced things, for instance, frameworks like Python and R, they build on top of a tool chain, and application software such as Chromax that is also built on top of a tool chain. So the key point here is that everything is consistent. So when a tool chain gets built, one picks a single version of a compiler, and everything is built with that version of the compiler to the very dot of the version. So you don't get any inconsistencies. And then half a year later, people start over, taking a more modern compiler, pick an MPI library, pick a current BLAS library, and build everything again. That is why when a service runs for a long time, you have many, many different versions of this tool chain. So the key thing is, so here are two key things. There are frequent releases every half year, every year, so you get pretty modern versions of everything included there. And on the other hand, we typically do not take versions away. So if you are established on a service which runs for a few years, you typically get a choice of continue of the toolchain version you have started your project with, or if you want a more modern one, you can choose a more modern toolchain. We explained that before. That's at the very bottom of the module system. That's the module system, once the service is running for some time, gives you multiple choices of versions that everyone can get what they need. Another thing of these tool chains is that it facilitates easy linking. So without the tool chain and the module system, you will have to tell the compiler for every library, for every bit you want, where it is, that the compiler finds it and can link it everything together. In this setup, these tool change setups in connection with the module system, everything in the system knows where the libraries are, which it has to link. So let's have a bit of a look. Available tool chains. So here I have started adding things for Arrhenius. This is picked out of the documentation. The main goal here is to show you a bit where we stand, what to accept when you get access to Arrhenius. The hardware of Arrhenius is very similar to Dardel. And a lot of, on the other hand, there are a lot of ideas which come out of what has been provided with Tetralid. So what you get, if you go look into Arrhenius, there are NAISS provided build environments, and these are very much based on the ideas which have been used on Tetralid. So if you are used to using Tetralid, perhaps that is where you want to look at. On the other hand, we also provide the Cray programming environment, which comes together with the hardware, since it is HPE, which bought Cray some years ago, but they keep the name Cray for a lot of things. So it comes dedicated with the hardware, and there's a lot of development effort. So with the NAISS provided tool chains, we currently have two major versions. There is the GCC provided ones, which are based on GCC 14.3. And here we have two versions. Most of that is the same. The key difference is that one is built on OpenMPI. So this is, if you're familiar with toolchains, this is based on FOSS 2025B in EasyBuild, which you find on many other machines, such as Kepner Kaiser or Cosmos or Pele. And then there is here this one, which provides MPitch as an MPI library. They use FlexiBLAS is an interface where you can change the BLAS library underneath, but out of the box, both of that will use OpenBLAS for the BLAS needs that you get fast linear algebra, FTW, and ScalarPack. When it comes to Intel provided toolchains, there will be two. There is one based on Intel 2003, that is based on the Intel 2003.1 release, and that provides the Intel Classic compiler. I will change a few, I will give a few words on that later. And here we have the Intel 2005 toolchain, which is based on the recent Intel 2025.2 release, and that uses the new Intel LLVM-based compiler. Both the Intel toolchain use the Intel MPI and Intel MKL for the linear. So Intel MPI, that is an MPitch derivative, and Intel MKL, among other things, provides you with BLAS needs, FSTW, ScalarPack, and a few other things. And these are module-based. Then we have the Cray-provided programming environment. And that is provided on Arrhenius as a container. And to activate that, you will have to use the NAISS-developed command HPC container shell. So here, this is Cray's programming environment. A few words on the Cray programming environment. As I said, we have that on Dardel. So on Dardel, with the Cray programming environment, CPE, you can load a CPE module like that. And based on top of that, if you want to use installed software titles, the latest versions are in this so-called PDC module. You load a module PDC. Birgitte said that before on Dardel, it is not advised to use a module purge. You can unload modules, you can swap modules, and you can load modules. And if you load a module which conflicts with something else, it unloads everything that conflicts. On Dardel, we have different compilers available. By default, you get the Cray compiling environment, commonly used as Cray compiler. You do that by ml proc environment Cray. As I said, that's the default. You can swap that for the GCC compiler with procenv GNU, and you have the procenv Intel and the procenv AOCC, which is an AMD provided compiler. Going forward to Arrhenius in the Cray programming environment, we will only provide the first two, at least for the beginning. I said that already as a default. When you connect, I can, if I have some time, I will show that later. The procenv Cray is loaded by default after login, and you can change that. Inside, you find the Cray libsci, which provides BLAS, LAPACK, SCALAPACK, and the Cray MPIG, which provides the MPI capabilities needed. If you want to use EasyBuild, there are toolchains which you can use in your EasyBuild recipes for Cray CPE Cray, CPE AM. Here's a typo. That is CPE GNU. Here's a typo. CPE AMD, that is for the AOCC, and CPE GNU, that is base for the procenv GNU. I will fix that after the lecture. So these are CPU things. As I showed here, these build environments, GCC, build environment Intel, these are ideas which have been deployed on Tetralid beforehand. If we go to GPU toolchains on Arrhenius, there will be NAISS provided toolchains, which are based on GCC 14.3. You load that by build environment GCC CUDA, as different from if you had it here, you had build environment GCC. So GCC CUDA, that is if you want to build a code for the GPUs on Arrhenius. That is the same GCC version. It uses MPIG, and then you get an OpenBLAS, an FFTW, a SCALAPACK, and NVIDIA provided libraries, NCCCL, a communication library, NVSHMEM, which is shared memory programming, and CUDA performance libraries. Alternatively, you can use the NVIDIA HPC. It's based on the toolchain NVHPC with CUDA, OpenMPI, and NCCL. Here you see there's a different BLAS component directly based on NVIDIA for the chips, and this is as above. The build environments can be loaded by the relevant modules. If you go into the Cray programming environment, in addition to what there was beforehand, you need to use the proc environment NVIDIA. You can get the proc environment NVIDIA, which so you get the choice. So here you get the choice of programming environments provided by Cray. In addition to what was there before, the Cray and the GNU, you also get a proc environment NVIDIA. Important remark on building for the GPU nodes. If you want to compile for GPU, that needs to be done on the GPU node. So for instance, with the interactive command, which we will show this afternoon. And the reasons are twofold. On the one hand, we have very different hardware on the CPU and GPU partition. The CPU partition is x86 based. There are AMD x86 processors, while on the GPU nodes, the host CPUs are ARM chips. Also, there are no NVIDIA drivers on the CPU node, so if you try to build CUDA code, it will just fail outright. So here we have a short summary what these are. So under Dell we have the programming environment Cray, GNU, Intel, and AOCC for AMD AOCC compiler. Going forward to Arrhenius, it will only be the first two. Then here on Tetralith there's GCC Intel, and on Kepler, Kaiser, Cosmos, and Pelle you will find FOSS toolchains, which provides the GCC compiler suite, Intel toolchains, which gives the Intel compiler suites, and then there's GOMKL, which is to some extent a crossbreed of these two. It uses the FOSS, it uses the GCC compiler, but uses MKL for the BLAS, FFT, and scalar pack needs. And you can load these. You can load these with a module avail FOSS. Here we have a screenshot from the Cosmos system at LUNARC from some time ago. After loading a toolchain, many new modules become available. I plan to show that in a minute, and use ML avail to see what is there. So a few more remarks on using toolchains. If you change a module or toolchain, the module system will try to give you give you versions of everything you have loaded before, which is consistent. So for instance, if you change a compiler, then it will try, and for instance, we have loaded an HDF5 IO library, it will try to find you an HDF5 IO library matching on the new compiler. But if that's not possible, so for instance, if it's missing, then you will get an error. Very important remark is that many of these things which are provided in toolchains or in modules built on top of the toolchains are also installed in the OS, but the advice is do not use them, because in particular if the service is a few years old, for instance GCC, which comes with the OS, will be old. In the toolchains you will get a more modern compiler which is likely to give you better code or have more feature. Similar for Python, there's always a Python in the operating system, but this typically gets not or gets rarely upgraded. If you want a modern Python, we highly recommend you to use one out of the module system. So let me just show a bit. We are here on Tetralith. If you log in, you don't get very much. So if you want to look what kind of build environments we have on Tetralith, this is, I pick while Tetralith is end of life, this is what you can expect how Arrhenius will look if you have if you're interested in the NAISS provided build environments. So I can, as we showed yesterday, I can just type tab and it will show you all the completions which are possible. And here, for instance, we can just pick the GCC 2023 B. So module show will show you all the actions what it will do. So this will load the FOSS 2023B module, which in itself has a lot of things. Another thing I want to show is ML-avail HDF5, which is an important I/O library, and currently you see something which lives at the very basic of tetralate. If I now load this build environment GCC and run that again, you see now I get here an HDF5, which is exactly built on this version of GCC and OpenMPI, which are included in this build environment. And if you need an HDF5, pick this one. First load the programming environment, the build environment, and then add the HDF5 module. This is the best match for the underlying environment. So when you want to compile code, this is for those of you which actually need to build code. On the Cray system, you irrespective of compiler, you on the Dardel system provided by Cray, and this is expected to hold if you use the Cray build environment or Arrhenius. If you want to compile standard C code, use CC to activate the compiler. If you want to have C++ code, you use capital CC, and if you want to use Fortran, you can use FTN. If you just look into tetralate, that is what is to be expected for Arrhenius with the NAISS provided build environments. You just, if you have a GCC build environment, you use a GCC for C code, G++ for C++ code, and G Fortran for Fortran code. That is to build serial code. Then if you have an Intel build environment on tetralate, it's currently there are only the so-called classic compilers based on the old Intel IPR installed, which is ICC for C code, ICPC for C++, and iFort for Fortran code. So this is to be expected if I just roll back. If you go for Arrhenius and pick this build environment 2023A based on the Intel Classic compiler. If you want to use the Intel, the NVVM compiler, sorry, wrong tab. We have listed that here. So here again, you have the how to invoke the classic compiler. And if you have the new LLVM-based compilers from Intel, that will be the new 2025 Intel compiler toolchain. On Arrhenius, you use ICX for C code, ICPX for C++, and IFX for Fortran code. So let's just show this a bit on Dardel. When I connect, I get that. And if I just do a CC minus version, I have here the POC-env Cray, and I have the Cray CCE compiler. No, come on. So you get feedback. It's Cray Clang compiler version 18.01, which we are having exactly here. And then you can use that to build your code. If I go for the POC-env GCC, it takes a moment. Let me just see. What do we get? It's GNU's. Apologies. So you see, it has now replaced the Cray compiler with GCC native and the POC-env Cray with the POC-env GNU. And so, for instance, the Cray libsci and Cray mpich, these are the MPI library and the linear algebra library. They have been replaced by versions matching on the GNU compiler. Previously, we had the versions matching on the Cray compiler. So here you can directly see how the module system tries to keep everything consistent, and this is set up that it can be working consistent. If I now do a cc -- version, and you see it is GCC 13.2.1. So we keep using CC to compile C code, but the CC activates a different compiler depending on the POC-env which you have loaded. The last thing I want to show is if you want to use, if you need to compile MPI code in the Cray programming environment that is unchanged from above, it's CC, capital CC, and FTN. I have just shown you for the CC. If you are going to use the NAISS programming environment, if you have a built environment with GCC, it will take MPI CC for compiling C code with MPI, MPI CCX for C++ code, and MPI Fort for Fortran code. That is irrespective of whether you have the OpenMPI or the mpich as an MPI library. And with Intel, if you have the Intel MPI library together with the Intel compilers, it's MPI ICC, MPI ICPX, and MPI iFort to invoke the Intel compiler if you have an Intel built environment. Okay, that is